Hi everyone. So in today's video, we are going to learn about distributed systems. So in this video, we are not going to go through the entire course of a distributed system that is taught in your university or in a semester. But it's generally for it's for people who are looking to learn distributed systems very quickly and they can just go through this video and learn about the basics of what distributed systems are and how distributed systems work at a fundamental level. So this is what the goal of the video this video is. So to explain what a distributed system is and or to understand how a distributed system works. So we'll take a simple example for this exercise, which is basically a hash table. So all of you are I guess familiar with how hash tables works and what is a hash table. So I'll not go into details of how to implement a hash table using arrays or hashing strategies, or how to use chaining strategy for resolving collisions in hash map, all those things. But I will take a simple hash table hash map library available in common programming languages. For example, in C++, example could be an unordered map, or in Python it could be a dict. I'm going to use this library. So given a hash table, for example, let's take unordered map in C++. So let's try to implement a simple hash table using unordered map in C++. Actually, I'll not implement it here, but I can it's a very simple exercise for anyone who wants to implement a map or a hash map or hash table in C++. So basically, the idea is that you have a library std unordered map, and then you have a pair of the data type for the key and the data type for the value. So generally, for this problem, let's say we assume that both the key and the value for this exercise are strings. So we can take both to be, let's say, std string uh, data types. So we have a hash map. Let's say I draw a kind of a table where we have keys as string and values as string. For example, A and value, let's say apple, B for ball, C for cat, and so on. So this is a very basic hash table that we have at this stage. So now, generally, what happens in very high throughput systems or systems in memory databases, where we have where it's we are storing key we are using the hash table as a in memory database. So in those scenarios, we can have complicated key value pairs for the hash table. uh, but the thing is that eventually while time goes, the size of the hash table increases beyond bounds. So let's try to do some calculations to understand whether a simple hash table can suffice our needs. For example, let's say right now, let's say our requirement is, let's say, 1 million key value pairs, 1 million kV pairs. Okay, and assume that each kV pair is of, let's say, size 16 bytes. Okay, yeah, let's say 1 million kV pairs, and it's each kV pair is of size 16 bytes. Now, how do you estimate the size of this hash table uh, in memory size? So one way is basically to calculate the number of bytes that it would occupy. So you have 16 bytes and you have 1 million of those. So you have basically 16 million bytes. 16 million bytes that would be taken up by the RAM. So how much is 16 million bytes? So if you do some basic calculations, it should come roughly to around, let's say, 15 MB, that approximately 15 MB in size. So as you can see, 15 MB is very much manageable on most of the modern personal laptops or desktops, having like around like 8 GB or 16 GB of RAM easily available. So 15 MB is nothing compared to those. Now, let's assume that we have one instead of 1 million key value pairs, we have 1 billion. So eventually, as I mentioned, that eventually the size of the hash map will grow beyond bounds. So it could reach to 1 billion at some point in time, right? So 1 billion. So 1 billion. So what would be the size of the hash table if we have, let's say, 1 billion key value pairs? And for now, let's assume that it's all key value pairs are 16 bytes in size. So if you do the math, you can see that from 1 million to 1 billion, if you go, we are like just multiplying by 1,000. So which implies that our size from 15 MB, it should go to around 15 GB, correct? So 15 GB would be the total size of the in-memory hash table. Uh, so now, as you can see that, as I mentioned, that most modern laptops comes with like 16 GB RAMs. So 15 GB is quite on the edge. And sometimes it 50 sometimes like storing this much amount of data is also not possible due to the system using some of the memory for swap and other processes. So probably storing 1 billion keys would not be a good idea to store on a single machine, laptop or a desktop. Moreover, thing like this, we are right now assuming that each key value pair is of size 16 bytes. But in many real life scenarios, so we sometimes many times we are storing longer metadata. For example, some flat files as values, or let's say some connection strings, and so on. So assume that on an average, if we have instead of 16 bytes, we have 1 kilobyte, 1 KB of data that we are going to store instead of 16 bytes. So if we have 1 billion key value pairs, each of 1 KB in size, so how much memory that would take up? So if you do a calculation, roughly that should come to around 1 terabyte. So as you can see, this is impossible, almost impossible to store on your personal laptop or desktop, or on a single machine, let's say on a cloud, because most VMs that are available in clouds like AWS or Azure, they come with roughly like around probably like maximum 256 GB of memory. So storing 1 terabyte is it's beyond its capacity. So in that case, how should we then store all this data? So we have to store this data, but our system is not sufficient to store this data. So how do you store it? So before going to how to store this data, I'll talk about one more point about why a single system like a personal laptop or desktop or a VM in single instance is not sufficient. Think in terms of the throughput. So, in many applications that require in-memory key value databases, the throughput requirements can be very high. Especially they are read-heavy applications, and sometimes throughput requirements could exceed more than a million requests per second. So, if you let's say if you do some basic math. So generally, I did some experiment on my personal system to understand what kind of throughput do I achieve with an unordered map. So I achieved kind of like 1 million insertions per second on an unordered map in C++. This is using a single core. So in many applications, it may be required to exceed this throughput. So it could be like more than 5 million requests per second are required. So in that case, our system is not sufficient to handle all this load alone. So that is another reason why we should avoid like storing all the hash map data in a single system. So now let's see how we can like mitigate this problem. So one way that we can mitigate this problem, as you might have guessed already, is to use multiple servers or multiple nodes, whatever you want to call it. So in that case, let's say for example, if our a single system is able to store, let's say 10 GB of data. Let's say we are storing 10 GB of data, 10 GB hash map on a single server. So if I use, let's say, five instances, so I in that case I'd be able to store 50 GB. So this is basic mathematical calculations that one should easily be able to do. That means like if we move to like five instances instead of single instances, we will be able to store five times of the data that I am able to currently store and service from a single instance. So so basically we are now going to a distributed setting. So now there are like several questions that would come to our mind while when I go to from a single system to a distributed system. So one of the question that obviously would come to my mind is, so just erase this a bit. So let's say I have in a distributed setting, what will happen? You have let's say five servers. Let's say I do not okay. So let's denote them as, let's say, S0, S1, S2, S3, and S4. Let's say instead of a single server, we have now five servers. Now the obvious question that arises is that earlier we are storing this single hash map in a single server. Now how we are going to store the same hash map in these five servers? So one obvious way is to basically partition the key value pairs. So there could be like multiple ways one could partition the key value pairs into these five servers. So one of the most intuitive ways to have equal partitioning. For example, let's say I just like equal percentage. Okay, let's say I have 100 key value pairs. So then each server gets to have like 20 and 20 key value pairs. So now we are storing each server is storing 20 key value pairs individually. Another possible partitioning could be to partition based on the throughput requirements. So as I mentioned earlier that the throughput requirement for a high volume application, a read heavy application could exceed 1 million requests per second. And even in those applications, there could be some keys which are very frequently accessed as compared to the other keys. So we could partition the keys in such a way so that each of the servers receive equal number of requests per second. For example, if we have, let's say, a requirement of 1 million RPS, so in that case, each server can then be allowed to would then serve 200K requests per second individually. So we can divide the keys in such a way so that each server serves approximately 200K requests per second. So the total request per second that we can serve from this overall system is 1 million RPS. So these are the like two common ways by which we can think of how to partition the data. Now, let's look at some of the common partitioning strategies that are widely used in the industry. The first of them is the hash-based partition. In a hash-based partitioning, what happens? It's very simple if you think it. So we have a key. For each key value pair, we have a key. Now we want to insert this key into the hash map. But the question is, where, in which of these servers will this key be inserted? So will this be inserted in S0, S1, S2, S3, or S4? So to determine that, what we do is basically we take some hash function on this key, hash of k, let's say. So hash of k, it returns some, let's say, some integer, some 32-bit integer. And what 32-bit integer, but we only have, as you can see, we only have 5 servers where we can where the key can go. So to reduce that space, so what we do is we do a modulo of n, where n is the number of servers. So in this case, n is equal to 5. So, for example, if our hash of k is, let's say, 24, and if I do modulo of 5, then my answer is 4. So, my key would then be inserted into S of 4. Similarly, during the querying phase, whenever we receive a key as an input, we want to search one of the servers for the key. So instead of searching all the servers for the key, we can do take the hash of that key and do modulo of 5. So if the hash of the key is, let's say, here is like we get the same key and we do a modulo of 5 and we get 4. So we know that our key is located in server 4. So we can directly go to server 4 and retrieve that value for that key. So this is pretty intuitive. Another popular way by which we can partition the key value pairs is to use a range-based partitioning mechanism. So what happens in a range-based partitioning mechanism is that we group the keys uh, basically based on certain prefixes. For example, let's say we group the keys from which starts with A to, let's say, M into one group, and we then assign all the keys that starts from with A to M. We assign all these keys to S of 0. Then we, like, say, N to Q, so we group N to Q into another group and we assign them to S of 1, and so on. So this is another way of assigning basically the keys to each individual server. So generally, for a hash table kind of application, a range-based partitioning makes little sense, because most of the queries that are going to be made are uh, not uh, range specific. For example, like I'm not going to query, let's say, fetch me all the values for keys where it starts from B to, let's say, D. I'm not going to query with some pattern like this. But mostly where the query patterns are random, so it could be that the keys that I'm going to query are random keys. So in those cases, hash based partitioning makes the most sense, because it does an unbiased partitioning of the keys into or almost equal partitioning, whereas range-based partitioning may not do a kind of equal partitioning, but we can force it to do. But a hash-based partitioning makes more sense in a hash table kind of application. So this is like these are the two of the like the popular strategies that generally distributed systems use for partitioning the data. So now, one obvious question that comes to everyone's mind is, now let's say, what if I add another server to this pool? So it could always be possible that my data, since my data is always increasing, so tomorrow there is a need that my key value pairs increases from 1 billion key value pairs to, let's say, 5 billion key value pairs. And I need to add, let's say, one more server to this pool. Let's say I call that S of 5. Correct. So one way, there are like generally two ways by which we can scale a system. In this case, our system is the hash table. So one way is scaling up, another way is scaling out. So in scaling up, what we do is we increase the configuration of the existing servers. For example, if our existing servers has 8 GB of RAM, then and later we find that 8 GB is not sufficient. We change the configuration of the server to 16 GB. So this requires basically like stopping the server, then restarting the server, because the configuration changes being applied. Another popular, actually more popular way of scaling is scaling out, where instead of changing the configuration of each individual server, what we do is we add more servers. So if we have let's say an 8 GB server, and we want to achieve a 16 GB RAM, so we add one more 8 GB server to that pool. So now we have a total of 16 GB of server. Correct. So that is what scaling out means. So in this case, we are assuming that we are scaling out this system by adding one more server, which is S of 5. Okay, now let's see what kind of problem that might arise after we add this server. So let's take the same example of, let's say, the hash of keys k is 24. Okay. So before adding S of 5, we had 5 servers, and we added this k key into to S of 4, because 24 modulus 5 was 4, so it went to S of 4. Now I added the new server S of 5. Now if you observe that we our number of servers has increased from to n equal to 6. So earlier we had n equals to 5, now we have n equals to 6. Now what will happen when we want to retrieve the key? Let's say we want to fetch the value for the key k. So what will happen? The system would then apply the hash of k, which would return obviously 24. Now then what it will do, a modulus of n. So n in this case is 6. So 24 modulus 6 is 0. Correct. So now it will try to find the key in S of 0. It will go to S of 0 to fetch the value for this key. But remember that our key went to S of 4 during the write process. So obviously our system is failing here. Why? Because we have added one more server, and due to that, all the calculations, I mean the hashes have changed. So to overcome these issues, there are one way is to basically like recalculate all the hashes. So what will happen, like so so we have, so if there are like 1 billion keys, so we have to recalculate all the hashes for this 1 billion keys and redistribute those keys to this 6 servers now, instead of the 5 servers. So that is another, that is a that could be a time consuming process. So in that case we have to might have to like stop this system or pause this system, and then after we have redistributed all the keys to the 6 servers, then we again can continue. And remember that this process of like redistributing of the keys will occur every time a new server is added. Also remember that if we delete that server, for example, tomorrow we saw that some of the, we do not require one server, like let's say one server is redundant and we do not have any requirement for it, and we do not want to pay for that server, and 4 servers is sufficient for our use case. In that case also you can see that if we, let's say, decide to remove, let's say s of one of the servers, let's say we decide to remove s of 2 from this pool. In that case we have n equals to 4 now. So 24 modulus 4, it is 0. So same as before, now we are again searching for this key k in s of 0, which is incorrect. So as you can see that whenever we are adding a new server or deleting a server from the existing pool, our hash calculations changes, and we need to recalculate all these hashes and redistribute all the keys again before continuing the application. So it obviously leads to some downtime for this application. So how do I overcome this challenge so that we do not have to redistribute all the keys? So so one of the popular mechanisms or algorithms that is widely used to overcome this challenge is using consistent hashing. Okay, so let's look at how consistent hashing works. So so let's say we have the five servers as before: S0, S1, S2, S3, and let's say S4. So we have these five servers that we had initially, and in our earlier scheme, whenever a key k was given as input, so what we were doing is like we were computing the hash of k and taking modulo of 5, correct, and then assigning depending on this value, let's say it's 4, so we used to assign it to s of 4, let's say. So in consistent hashing, what is different is that in consistent hashing, both the servers as well as the keys are projected onto the same hashing space. So what this implies is that, for example, each server can be uniquely identified by the IP and the port. For example, S2 will have some IP port, S1 will have some IP port which are unique to that server, correct? So what we do is we take the hash of each IP port for each server, and then do a modulus of some value n. So, for example, if I for S2, if I take the hash of IP port and do modulo of n, we'll get some number, let's say x. So this becomes the hash of this server S2. So first question is like, what is this n? So we can choose n to be a sufficiently large number, such that it is larger than the maximum number of servers that we are going to use for our application. Let's assume that in our example, let's say n is let's say 500. So we are not going to use more than 500 servers for our application. So so for example, for this problem, let's say S0 has this value of hash as, let's say, 10. S1 has, let's say, 22. S2 has, let's say, 37. S3 has, let's say, 60, and S4 is, let's say, 135. These are just examples. So like all the values should be between, let's 0 to 499, because we are doing a modulus of modulo with n equals to 500. So now we have found the hashes for these servers using the IP and port. But now the question is, how are we going to assign these the keys to these servers? So the way the keys are assigned is that for a given key k, we apply the same hash function on that key and take modulo of n, which is like same as 500. So in this case, we take hash of k and do a modulo of 500, and let's say the value that comes out is, let's say the value is 15, okay, after doing a hash. So now we see that we do not have any server which has a hash value of 15. So then how do we assign this key? So we assign this key to the server which has the next greater hash value. So in this example, if you see that S1 has the next higher hash value of 22, which is greater than 15. So K is assigned to S1. Similarly, if hash of key modulo 500 was, let's say, 100, so in that case, if it was 100, so it should be assigned to s of 4, because the next greater value greater than 100 in among all the servers is 135, which is s4. So that key would be assigned to s of 4. Similarly, during the querying phase, whenever we get a query as a query key as an input, we do the hash of k modulo of n, and depending on which is the next greater uh, server having the next greater hash value, we go to that server and fetch that key from that server, the value for the corresponding key. So this is how basically the consistent hashing works. So another important thing to remember is that in consistent hashing, the hashes are arranged in a ring. So in this case, it is a ring like structure. So for example, so since we are taking a modulo of 500, so it could be well possible that the hash of our key modulo n is, let's say, 200. Let's say it's 200. Okay. So if you see, like, none of the servers have a hash value which is greater than equals to 200. So then which server this key should be assigned to? So since we see that this is a ring like structure, so that this key which having a hash of 200, it should be assigned to s of 0, because uh, the next greater value in that ring is s of 0. So since this key should lie in this region between s of 4 and s of 0, so that key should be assigned to s of 0. So this is how keys are assigned to servers in consistent hashing. So this brings us to the question that how does consistent hashing improves upon our previous strategy of like a simple hashing based mechanism where we are like assigning each key based on the hash to that corresponding server instead of like, finding the next greater server. So in our earlier example, we saw that whenever the number of servers changed from 5 to 6, the hash value changed for most of the keys. So in the simple hashing strategy, almost like more than 90% or almost 100% of the keys has to be redistributed among all the 6 servers. But in this consistent hashing algorithm, if you see carefully that all the keys that are located between S0 and S1. So let's say we add a new server to this pool. Let's say we add a new server S of 5 here. Okay, and let us assume that the hash of this S of 5 is, for example, let's say 230. Okay, so let's assume that the hash is 230. So now let's see like what happens to the keys. So for all the keys that are located between S0 and S1 that are having hash values which are greater than 10 and less than equals to 22. So for all those keys, they are still assigned to S of 1. Why? Because S of 1 is the next greater server having a next higher hash value. Similarly, for all keys between s of 1 and s of 2, which are having hash values greater than 22 and less than equal to 37, all those keys are still assigned to s of 2. Similarly, all the keys between S2 and S3 are still intact. S3 and S4 are still intact because none of these key, like the next greater value have not changed for all these keys. Now let's look at the all the keys between S4 and S0. So all the keys between S4 and S0 have the hash value of greater than 135 and less than equals to uh, 10. So this is less than equal to 10 because since it's a ring like structure, so you can assume that you can add n to this number. So it could be like 500 plus 10, which is 510. So all hashes that are having values like greater than 135 and less than 510 are assigned in this region, and they're assigned to s of 0. Now, when we introduce this new server S of 5 having a hash value of 230, so you can see that all keys that are having hash value of less than equal to 230 but greater than 135, so they are still assigned to S of 0. But when we add this new server S of 5, this the next greater hash value should be 230, all because it is the next in the ring. So when we are going to when we get a like a get query for this key, the same for example a key having a hash value of, let's say, for example 200. So for a key having a hash value of 200, we insert it initially to s of 0. Now when we are querying this key after we add the new server s of 5, uh, we are going to query that key in server s of 0. But this is like, if you can, it's you see that the next greater hash value should be 230. So the system would then go to s of 5 to query this key, correct? But it will not find this key, which is incorrect, because our key is written to s of 0, but we are querying in s of 5 to find that key. So this is incorrect. So how do we overcome this problem? So one way is to like redistribute all the keys between s4 and s0 in such a way that all the keys having hash value of 135, greater than 135 and less than equals to 230, are assigned to s of 5, and all keys which are like greater than 230 and less than equals to 510, though those are assigned to s of 0. So in this way we can overcome this problem. So you might ask, like, it's still like we are redistributing the keys, because we are redistributing the keys in this region s4 to s0. For all these keys we are redistributing to s of 5. But if you see that in our earlier example, we were redistributing almost 100% of the keys to all these servers. But in this algorithm, we are redistributing only m by n fraction of the keys. So what is m? So m is the number of keys, and n is the number of servers, for example. So n is the number of servers. So if you assume that all the keys are equally distributed among these five servers, so then each partition, like all the region between S0 and S1, this should have m by n keys. So if my n is, let's say, 100 and n is 20, so in it, all so we can assume in case of equal partition that the region between S0 and S1 contains 20 keys. Similarly, the region between S1 and S2 contains 20 keys. Here it's also contains 20 keys, and so on. So ultimately, we are redistributing only 20 keys among out of 100 keys. So which is like 20% of the keys that we are redistributing, and which is like much less as compared to our earlier strategy, where we are registering almost 100% of the keys. So this is how consistent hashing helps in activating this problem of like redistributing all the keys and reducing the downtime associated with redistributing the keys. Let's look into now another problem that might come while we are implementing this consistent hashing algorithm. So one of the assumptions that we earlier made is that the keys are uniformly distributed among the servers, right? So we assume that among the 100 keys, if they are distributed into five servers, each server should get roughly 20 keys. Correct. But in most real life scenarios, since hash values are random in nature, so it is not always this case. So it might happen that 99% of the keys out of 100 keys are assigned to S1, and only 1% of the keys are assigned to the remaining servers from S0, S2, S3, and S4. So this is a perfectly valid scenario in many real life applications. In such a case, as you can see that if we add a new server between, let's say, S0 and S1, let's say having a hash value of, let's say, 12. So since S1 has been 22 and S1 S0 has to 10, so let's add a new server which is having a hash value of 12. So in this case, we see that 99, we are again back to that case where we are like redistributing 99% of those keys, because 99% of the keys lie between S0 and S1. So how do I handle this problem then? So one common strategy that like people generally use to handle such a problem is to use virtual locations for the servers within this ring. So what do I mean by virtual locations of the servers? So when we are taking a so when so for each server we are assigning a single hash value in that ring. So instead of assigning a single point to that server in that ring, we assign multiple virtual locations for that server within this ring. So, for example, let's say for S of zero. So, for S of zero, what we can do is, let's say we want to add, let's say v equal to 100. So, for each S, we add 100 more virtual hashes within this ring. So, we can do for S0, we take the hash of, let's say, the IP port, and we append, let's say, uh, uh, an ID, implementing ID, which is, let's say, V1 to 100 for the 100 servers. And for each of this ID, we take a hash and do a module of n. So after we do that, we can see that we will get 100 different hash values, 100 hash values for each server, for each SI. So in that case, each server is assumed to be located at 100 different locations in this ring. So so these are like virtual locations, because like we only have a single server, but we have 100 different virtual hashes. So then how do I like hash the keys? So the hashing of the key takes place in the same way. So we find the hash of the key and do a module of n, and then assign it to the next greater server in that ring. So in this way we can somehow guarantee the uniform distribution of these keys, that each server is approximately taking in equal number of keys among all this like key space. So now we understood how consistent hashing works and how does it improve upon the existing simple hashing mechanism. So let's look at another associated problem when we are partitioning this data using a consistent hashing strategy. Okay, let's clear the screen a bit so that it's easier to understand. So we have say uh, we assume that we have five servers. Okay, so we have S0, S1, S1, S2, S3, S4. Okay, so now what happens, like in an application, like you have, like, generally for a hash table like application, you would have two different kinds of APIs. So one API would be for insert uh, KV. So insert this KV pair into the hash table, and another operation could be get key. So it's like uh, fetch me the value for this key. Okay, so generally, when a client is connecting to this service or this application, a client is not aware of how many servers are there, or like how the consistent hashing algorithm is implemented, or like which server is storing which key. So client is agnostic of all this information. So client only, let's say I am a client computer here, and I want to, let's say, insert a key value pair. Let's say insert. Insert let's say 40 comma 100. So the key is 40 and that's the value is 100. or let's say not take a integer value, let's say take some string. So let's say my key is a, and my value is apple. Okay, let's say a and apple. Okay. So now when the client is going to connect to this application, it will communicate with only one of these servers, right? So for example, let's say the client communicates with S of 1, because it could be that S of 1 is the nearest server to this client. So it's, the client sends this uh, API query that insert a and apple into this hash table, and then S1 receives this API call that we need to insert this key value pair with the keys A and value is apple, and then it goes and finds that hash of the key and does a modulo of the n. So let's say S1 does this operation and finds that hash of A, where A is the key, modulo n is, let's say, 40. S1 finds that the hash is 40, but note that S1 has a hash value of 22, correct? So you can see that that 20, since 22 is lower than 40, and uh, thus which means implies that A will not be assigned to this server S of 1, and then S of 1 needs to find which server should store this key. So then if you see that in this ring, so you can see that S of 3, which is having a hash value of 60, so which is like the next greater value than 40, it should store this key A. So the next step would be for S1 to be is to forward this key to S of 3 and say, okay, S of 3, store this key value pair in your system. But how the servers are going to communicate with each other, so how they're going to send this message, or how they're going to know which like which are the servers in this consistent hashing ring, and what are the hash values, so that it can forward the key to the correct corresponding server. So there are multiple ways in which the servers can store this information. Okay, so let us look into some of the ways in which the servers can store this information. Okay. Let's say the first possibility is that each server stores a table. Assume this there is a, like a, it's a kind of a another hash map for each server, where it stores for each server S of I, what is the hash value, and let's say the IP and port number of that server. So for each server has this table associate in its own memory, for example. So now, so S1 has this table where it knows for S1, S0 what is the hash, for S1 what is the hash, for S2 what is the hash, and so on. So, and also the IP port for each of the servers. So then what S1 can do is, like, whenever it receives this key, it will find the hash value, which is in this case 40, and then it will find the next greater hash value from this table, which in this case is S of 3, and then it would create a connection with S of 3 using the IP port provided in this table, and send this key value pair to S of 3, and say that, okay, S of 3, this key is for you, and you should store this key. So this is one way by which you can uh, forward these messages. Okay, so in this approach, if you see that we are storing a table with all the servers and their hash values. So if there are n servers in this pool, so if we implement so basically we are having a space complexity of O of n, first of all, because we are storing all the details for this n servers, and then we are finding the next greater server. So the next greater server can be found if we implement this table as a let's say a sorted list or a red black tree or an avial tree, then we can easily find the next getter server, and that time complexity would be like O of log of n to find the next getter server. But importantly, note that we are finding the next getter. We are like forwarding it in a like constant like O of one time complexity to the corresponding server, because we can directly find that which is the next server, which is S of 3, and forward it to that server. So my time complexity for forwarding to the correct server is O of 1 with this data structure. So generally, like for smaller, let's say where the number of servers are less, where n is like very low number, like 500 or 1,000, this strategy is fine, because even if, let's say, tomorrow we a new let's take this case where a new server is getting added. So when a new server is getting added to this pool, let's say S of 5. So what does it do? So when it gets added to the pool, so it must send some kind of message to all the existing servers in this pool, saying that okay, I have joined this pool, and this is my hash, and you can start sending me any message or any keys, corresponding keys that is like having value lower than my hash to me. So S5 will like send like a message to all the servers. So when a new server joins, it sends O of n messages to all the other servers in this pool, and also it will create its own like table of the server and the hash along with the IP port. Okay, so this is how you can implement like a simple solution for this problem of routing, where the client connects to one of the server, and the server then forwards the request to the correct server that will store this key and get the response back and send this response to the client. So this is one way how we can do it, where we are using O of n space, and but my time complexity for forwarding the request is O of 1. In another strategy, what we can do is, instead of like knowing about all the servers in this pool, for example S1 knowing about S0, S3, S2, S4, S5, and so on. So it only is concerned about who are the previous and the next servers in the consistent hashing ring. So for each server S1, it's clear. So if you take S of 1, in this case it has only two entries. So if we do S of I, H of I, and IP port, it has entry for only S0 and S of 2, and H0 and H of 2, and IP, similarly the IP ports for S0 and S of 2. So it did not store the details about all the servers in this pool, that is like the O of n number of servers, but only the predecessor and the successor of itself. So in this way, how does routing will take place? So in this example, in this case, when a client sends a request to S of 1, and S of 1 finds that the key has a hash value of 40, and but it has a hash value of 22. So it says that the hash value is greater than itself. So what it will do is, it will forward the request to its successor. So in this case, it will forward this request to S of 2. So now S of 2 receives this request, because remember that S of 1 has knowledge about only S of 0 and S of 2 and no other server. So it can only forward to S of 2. So now S of 2 receives this key from S of 1, and it says that it has a hash value of 40 and it has hash value of 37. So now it must again like forward it to its own successor, which is S of 3. So and when it comes to S of 3, S of 3 finds that okay, this hash value is corresponding to its own hash value, and so it must be stored in its own server. So now it is then stored in its own server, and it is not further forwarded to other servers. So this is how the routing takes place. So as you can see in this strategy, we have although we are having a table that is stored in each server, that having a constant space complexity, but the routing has a complexity of O of n, because in the worst case we might need to route the request to all the n servers, because it could be that S1 forwards to S2, then S2 forwards to S3, S3 to S4, S4 to S0. So till it can go through the entire circle. In that case, the routing complexity is O of n. So this is a trade-off. So the trade-off is that when we like reduce the space complexity for storing the information about the remaining servers in this pool, we lose in terms of the time complexity of forwarding the request to the correct server, and also the latency in responding to the client. So that is another trade-off, basically, to for this strategy. There are like other strategies that can help with overcoming kind or finding a middle ground here. So that algorithm is known as chord algorithm. So what happens in chord algorithm is that, so in CORD, what happens? Each server stores a table similarly, but it does not store all the does not store details about all the servers, but it stores details about like the servers based on like uh, like which are like, let's say a server has a hash of, let's say, h, for example. So it will store details about those server which are h plus 1 distance, at least h plus 1 distance from it, then at least h plus 2, then at least h plus 4, h plus 8, and so on. So basically, if we have, like, say, if you are storing if you are representing the servers with k bits, so we have like h plus 2 of k, and definitely we have to take modulo of this with the n, which was the n value that we earlier considered to be 500. So for each server, we are storing only O of log of n numbers of entries, instead of O of n entries for a like a full table, or O of one entry for only the predecessor and successor. So this is kind of like doing a binary search, if you think in that way, because which has a space complexity of O of log of n. uh, also it has to keep knowledge of the not only the like the h plus 1, or not only the successors of the server like h plus 2, but also like the predecessor h minus 1, h minus 2, and so on. Why the knowledge about the predecessor servers are also required? Because when our new server is added, so it must send RPC message or some kind of message over socket to all these servers which are predecessors h minus 1, h minus 2, h minus 2 to the power of k, and so on, to and say that, okay, guys, you add me in your entry table that I am located at this distance. So it needs to know about these servers also. So it's basically O of 2 of log n entry size of entry table that we are storing. But then how does the routing happens? So in this chord like algorithm, how the routing happens is that whenever, let's say, s of 1 receives this key, with a key as a and value as apple, it finds the hash, and it finds the next greater, let's say the hash was 40, and the next greater, it finds the next greater like h plus 2 to the power, let's say q. Next, so for some q, it finds the next greater value h plus 2 to the power q, which is at which is lower than 40, but it is like the it is the highest, it is the maximum value lower than 40. So it then finds the server associate next server associated with h plus 2 to the power q. So in this empty table, it finds the which is the server corresponding to h plus 2 to the power q, which is like less than equal to 40, and it forwards that message to that server. Let's say I call it the s of q, and it forwards that message to this server s of q, and from there it either s of q adds its own hash table, or it forwards further to downstream server using the same strategy. So this is how basically the quad algorithm works. So in this case, as you can see, the routing steps also has O of log n steps. So now you have seen like there are three strategies where we are doing basically we are doing a trade-off between the space complexity of storing the entry tables for the servers, and the routing time complexity. So we had O of n earlier. The first one we saw having O of n space complexity for storing the entry table, but O of 1 time complexity for routing. Whereas in COD, you have O of log n space complexity for storing the entry table, but you have O of log n time complexity for routing the requests. So this is how basically routing can happen. So there are other algorithms that you can look into for what researchers have come up with for like for optimizing the routing and the space complexity trade-off. There are still some questions that need to be answered in this strategy. For example, how the servers are going to communicate with each other. One possible strategy is to basically like send and receive messages over the socket. Other possibilities are using RPC, the remote procedure call. So, Google has a very good library for this gRPC, so which uses the protobuf protocol for serializing and deserializing the messages during the communication phase. So these are like some of the important things that should be kept in mind while implementing a solution similar to this consistent hashing, where we are or in a distributed network where there are like multiple servers communicating with each other over this network. Yeah. So another interesting like question that generally comes during design of distributed systems is that how does the servers handle like multiple clients? For example, you have like several clients connected to this application at any particular instant of time. Like for example, you can have let's say 10,000 clients or 100,000 clients connected to the application. So how does the server handle all this load by itself? You can see that like whenever a client is connected, it sends a message request. For example, either insert this key or fetch the value for a particular key. So if you like if each server starts to like serve each client sequentially, so then it could be that like one client is waiting forever for receiving its response, while some client while the server is working on serving the request for some clients which was previous in the queue. So a queue based model for serving like requests would not ideally work in such a scenario. So one possibility is to use basically threading. So generally, like servers, what they do is they can use they can spin up multiple threads or multiple process to serve to handle each request from this clients. Generally, when let's say for example n clients are connected, so the servers can spin up either new threads for each new client, or they can create a kind of a thread pool where let's say a pool has let's say 100 threads, for example, and whenever, let's say, so at any particular instant of time, 100 threads would be working. So the concept of like threads working in parallel is pretty like complicated, because not all systems support like parallel execution of threads. So depending on, and it also depends on how many like CPU cores are available in your system. For example, if there are like if your machine is like a 4 core machine, then at any particular instant of time only four of the available threads will be working in parallel. The others are other threads, although are active threads, but they are not actually working in parallel, but they are working in a concurrent fashion. So what do you mean by concurrent fashion is that, so let's understand what concurrent execution of thread implies. So in concurrent execution of threads, what happens is that, so let's say there are like three threads, T1, T2, and T3, and only like two of these three threads can work in parallel. So I have, let's say, five tasks, and I label them as, let's say, A1, A2, A3, A4, and A5. Okay, so I assigned like T1 is working on A1 and T2 is working on A2. So this two tasks are being worked on in parallel by T1 and T2. Now it might happen that while let's say T1 is working on A1, there is some process that involves doing some IO over the network. For example, let's say the tasks could be like doing insertion into this hash table. So for example, A1, A2, A3, this could be five tasks for five insertions into the hash table. And during the insertion phase, what might happen, like when a server is like accepts a request from a client, it will either be involved in inserting that key into its own hash table, or it is going to forward that key to another server and wait for the response from the another server for that insertion. So it could be that, like in this process of where T1 is taking a task A1. So A1 task, it involves forwarding request to another server. It's forwarded, and it's waiting for response from that server. Meanwhile, then T1 would be sitting idle. So in this phase, what can happen? The operating system can schedule the next task, which is, let's say, A3 to T1. So now, as you can see that T1 is now responsible for two tasks, but both the tasks are not happening in a parallel fashion. So it is first thing is that it is waiting for A1 to receive response from the server that it has forwarded the request, and on the other hand, it is now taken up task A3, which is like initiating another insertion task. So in A3 also, it could happen that A3 either does like insertion on own server, own machine, or it forwards the request. Similarly, for T2 also, it can happen this same. So as you can see, whenever basically a thread is idle, that is so the task that it is handling is some kind of IO related work. For example, an IO over the network. For example, to sending and receiving messages through socket or RPC, or an IO over disk. For example, writing some data to a file on the disk, or reading some data from file on a disk. So these are like IO intensive tasks, and at that instant, the threads might sit idle for some time, and during that time, the operating system can schedule another task on that thread for that thread. So it might appear that these tasks are being handled concurrently. So this is what concurrency means. So this is one way by which a single server can handle multiple clients concurrently. Like if I have 1,000 clients connected to a single server, so for some of the clients might be waiting for response from for the request sent forwarded to other servers, while for some of the clients the server is initiating requests. So this could happen in concurrent fashion. So this is one way by which servers can handle concurrent clients. But the problem, as you can see, is that creating threads or handling multiple threads, because like threads are expensive, and many times context switching happens between threads. So context switching is something that I discussed just now, that whenever a thread is working on one task, and then the operating system schedules another task on that thread when it is sitting on idle. So it is a switch in the context, and the thread has to keep a stack of all the variables, the functions associated with each of these tasks. So it's like an overhead for the threads. So creating and destroying threads is quite expensive on like limited amount of RAM for some of the servers. So what alternate strategies can then servers utilize? So one of the well-known strategies that servers can use is basically using uh, select or epoll. So for example, if the servers are communicating over socket, so the socket library exposes a useful function which is known as select. So what the select does is, in select, so it returns three different types of file descriptors. File descriptors are nothing but, you can think like, these are basically files or connections, different types of connections from other servers or clients. So the three different kinds of connections possible could be, like some connections might be waiting for sending a response. So these are known as the write FDs. Basically, they are waiting to send. They're waiting for the current server to send them message. Some are like read FDs. What are read FDs? Basically, they have these are connections where the other server has sent message to the current server, and the current server is expected to read these messages. And another type is basically exceptions FD. So these are connections which has caused exceptions. So we'll not get into the details of the exception FDs, but we'll mostly be concerned about the read FDs. So as you can see, like using select, so I need not have to bother about let's say using multiple threads to know which client is actively, let's say, initiating a request, or which client is waiting for response from a different server, and so on. Because when calling this select will return me a list of read FDs, from which I can read response from other servers or other clients. So using this, I can serve, let's say if multiple clients are connected here, that means like this multiple clients are waiting to say, so the current server is waiting for multiple clients to send requests to it, and I can just read all those FDs from file descriptors from this select statement and serve the request. So this happens within a single process only, and it does not require creating multiple threads, because threads are expensive. So this is one solution. Another solution that people commonly use is using epoll. So one of the limitations with select is that it can only monitor a limit of 1024 file descriptors. So if there are more than 1024 clients or connections that wants to connect with the current server, so it will not monitor those open connections. It has a limitation of only 1024. But with epoll, it's not, there are no such limitation, and epoll can monitor any number of active connections that are pending for like serving request or sending write messages and so on. So using this like two methods like select and epoll, one can overcome the difficulties or the issues that are inherent with multi-threading. So yeah, another important question that I'm going to ask is basically like, what will happen like when any of this server in this pool, let's say, is not responding, or it's let's say that is like too much load on one of these servers, and it is not responding in time, or it has crashed in the worst case. So how will the other servers know, and how does the ring connect itself in that case? So one possible way that you can imagine that how the ring can heal itself is that, or first thing is that how to detect, let's say, the server is down. So remember that each server is like has an entry table for assuming that we are implementing a chord based algorithm. Each server has entry table for h plus 1, where h is the hash uh, it's of itself, h plus 2, h plus 4, and so on, and also h minus 1, h minus 2, and so on. So what can this server with a hash of h do? It can send periodic heartbeats to all these predecessor servers. For example, it sends a heartbeat message, let's say every second to h minus 1, every second to h minus 2, and so on for till h minus 2k. So it sends heartbeat message to like all these O of log n servers periodically, let's say with period of 1 second. So what can happen now is that, let's say, if this server, let's say this s of I, this server goes down and is not responding, and if it's not responding, it is not sending these heartbeat messages to these servers h minus 1, h minus 2, and so on. So this servers now detects that they have not received the heartbeat from s of I. So remember that when s of I is sending heartbeat messages to h minus 1, h minus 2, or it is sending a join request to this h minus 1 servers. So these servers have already added s of I in their entry table. So h minus 1 will add s of I to h plus 1. So if h minus 1 has it has of h prime, so it will have h prime plus 1, which corresponds to s of I, and similarly for the others. So it knows that s of I is not sending heartbeat messages, so this server must be down. So uh, so uh, so what can then these servers do? So along with the heartbeat messages, so s of I, what it can also send is the its own successor. So since s of I is storing information about h plus 1, so s of I can send the details about h plus 1 along with the heartbeat messages to all these servers. So now when let's say these servers detect that, okay, s of I is not responding, or not sending the heartbeat messages, then it knows that s of I is, let's say, dead. And what it can do, it knows that the successor of s of I is h plus 1. So what it does is it replaces all entries in their own hash table, wherever the entry corresponding to s of I, with this s of I successor, which is, let's say, s of I plus 1 having hash of h plus 1. So this is how one can the servers can identify which other servers in this network are dead or is not responding. This is one way where how can we handle this situation. Okay, now let's come to a completely different problem of what happens when it's not entirely different problem, but it's will go into a different track altogether. So what happens, let's say, when a server is crashing, or it's crashed, or it's not responding for some time, or it has gone down and it has done on some and it requires some restart. So remember that we are working with in-memory hash tables. So with any in-memory system, so whenever the system is restarts, or it's crashed, so all the data that is stored in memory, it gets lost. So whatever a hash table data that a particular server has stored in its memory, that is lost once the server crashes or restarts. So let's clear this one. Okay. Um, So whenever a server restarts, the data it has in memory, it gets cleared. So how do I? So for a system which requires us to like available all the time, and also like does not like let's say has a strict requirement that no data should be lost. So how do I handle such a situation, like basically a high availability system? So in this case, what we can do is basically we can implement something, something known as persistence, or an write ahead log. So in this approach, what happens is that whenever a server requests receives a request for let's say insert operation, let's say, and it is the server that is responsible for storing this key. Let's say it's SI. So what will happen? So S of I will first write an entry in a log file. So a log file is basically, this log file is basically an append only log file where new entries are written at the end of this file. Basically, it's an append. New entries are appended to the end. So whenever insert query is made, so the a new entry with the key value pairs is entered along with the timestamp into this log file. So this log file is stored in disks. This is not stored in memory, but it is stored in disk for persistence. And after this entry is made in this log file, then the server will update its in-memory hash table for and it's update the key value pairs in the hash table. So now, if you see that, let's say this server crashes, the SFI is crashes. So what will happen now? So how will then SFI will recover all the like lost key value pairs that was stored in its memory? So whenever the server, let's say we start the server again after it has crashed, so it can start reading from this log. So it will open this log file. It will read all the entries from start to the end. So there could be duplicate. Remember that there could be duplicate entries or redundant entries, but it doesn't matter. So if we replay this log from start to end, so it will reach a state which is consistent with the final state of this hash table. So that is only thing what matters. So once the server restarts, so it replaces all the logs, and for each entry it creates a entry in the hash table. And if a new entry comes in the later in the in the log file which updates that value for that key, it's okay. So that key would be overwritten here in the in-memory hash table. But we are storing all the events associated with this server, not only the final event. So it might have you might think that for a given key k, so if the key k has been updated, let's say 5 times, so in the log there would be 5 corresponding entries. And if you replay this log from start to end, so the final entry would correspond to the latest entry. uh, we are not only storing the latest entry because it is then difficult, because if we have to, let's say, only store the last entry, so then we have to do a deletion operation on all the previous 4 entries. So remember that doing IO operations on files that are residing on disk are expensive operations. So we do not want to waste unnecessary, let's say, CPU cycles to like do this deletion operation. When we can like replay this log anytime the server restarts and can get to the final state. So this is how basically the systems can recover itself from a crash. But is it sufficient to have this write ahead log to ensure a highly available system? Observe that during the time that the server goes down and the time when it starts up again, so the system is unavailable. Why? Because all the keys that were sent during this time interval when the server was not running or not fully functioning, so during that time interval, all the keys that were sent to those servers would be either not inserted into the server, or they will be retried multiple times over until the server starts and starts functioning again. So the server is like not highly available system, if you observe it carefully. So, how do I go about making it a highly available system? Knowing that okay, at any time, any of this server, one or two, like even all of these servers can have malfunctions or can crash. Write ahead log is useful when the server is recovering from a crash. In that case, all the data that was there in the server before the crash, it can recover those data from the write ahead log. But it's not sufficient to ensure a highly available system. So how do I go about like ensuring a highly available system? So one of the very intuitive solution is to have like multiple replicas for each server. So what do I mean by multiple replicas of each server? Let's clear this screen a bit so that I can clear it entirely. Okay. Let's draw the servers again. Let's say I draw one of the servers. So in let's say I have a server s of I. So if the server goes down, so then that during that time, when the server restarts again, the system is unavailable as I described earlier. But what if I have like multiple copies of the same server? So what do you mean by multiple copies? So there will be like multiple servers, uh, but that all these servers will have the same copy of the data as in SI. For example, if SI has let's say three replicas, so in that case I will have like three replicas like this: SI of one, then SI of two, SI of three. So I have three replicas for S of I, and all these three replicas of S of I share the same data that is present in S of I. So when I say data, it implies both the in-memory hash table plus write ahead log. So this is what I mean by data. So all the three replicas, they have the same version, same data as this hash table and write ahead log. So this is what basically a replication means. So now think that if even if let's say s of I, this server goes down, for example. If this server goes down, so then the system, what it will try to do, it will try to forward that request to one of these replicas, si1, si2, si3, and so on. So like since like the probability that all of this, like the four, let's say the four servers going down at the same time is much less compared to at least one of the server going down. So taking into account that probability, so at least like one of these servers would be working or functioning properly. So in that case, the system is like likely to have a high availability. So this is how we can ensure high availability using a replicated system. So now let's try to understand a bit more about replication. So there are like few things that that is like challenging while implementing a replicated system. First thing is that how do I ensure that all of these servers in this replica have the same data? Why? Because think in terms of this scenario, that I am like inserting the keys to this hash table, and this is one of the partitions. So this is like this is a, let's say one partition, let's say p of I, and by p of I has, let's say generally in replicated system, the number of replicas are in odd numbers. So we'll assume that we have three replicas, not four. So I'll delete one of this and just okay, and rename it to S of I1. So S of I1, S of I2, S of I3. Okay. So now I have for this partition I have three replicas: S of I1, S of I2, and S of I3, and all of these three ideally shares the same data, the hash table as well as the write ahead log. But observe that, like, when I'm inserting a data here, let's say I'm inserting the data into S of I of 1, correct? And after S of I of 1 receives this, let's say, the key value pair, it inserts it in the write ahead log. First it will insert it in the write ahead log, then it would update it the its in memory hash table, and then it would then sync S of I2 as well as S of I3, correct? So now think like in this scenario, that what will happen if just after inserting my key here, key value pair in the S of I of 1, S of I of 1, let's say, starts like after it inserts the key here, it like it is malfunctioning, or there is like it starts to receive too much load, and this S of I2 and S of I3 are both are not updated in time, and it is taking time to update this to servers. So like when I make a gate query for the same key again, like the key which I inserted just now, I'm making a gate query for the same key again. Now it's the system finds that S of I1 is not working properly, so it will try to send the route the request to either S of I2 or S of I3. Now see that both S of I2 and S of I3, they were not replicated in time, and probably the replication process is still in progress. So when it goes to get this key from either I2 or S of I3, it will not find the particular key, and it will return an empty result, which is incorrect because we have already inserted the key before this get query using an insert query, and I'm trying to fetch the value for this key using this get query after this. So it should ideally return me the value for this key, but it is not happening because there is a lag in this replication, since it's the system has gone down, S of I has gone down. So this is one of the like problem that like commonly arises in many distributed systems. Okay. So yeah, so this is one of the problem. But how okay, so then another problem is that, let's say, in this example, let's say there is a like a load balancer kind of architecture. For example, what do you mean by load balancer kind of system? Let's say I have so instead of like inserting all the like key value pairs into one server, let's say S of I1, I randomly choose one of these servers, like one of these three servers for insertion. For example, I randomly, let's say, for inserting key value pair K1 V1, I choose S of I1. For K2 V2, I choose S of I2, and so on. So the servers would be chosen randomly. But observe that it can happen in a scenario. For example, I am so let's say I have the same key. Let's say A, okay, A, and I am inserting if A and Apple as the key now for in S of I1. Okay, now in the next query, I'm trying to update A for, let's say, aeroplane. Okay. Now, but remember that it is expected that when I'm inserting this query, all the servers are in sync. But it might happen that when I am inserting this query A for Apple key value pair, uh, both S of I2 and S of I3 are not updated in time, and it's still in progress. Now, A for aeroplane, this next query goes to S of I2 for insertion, and S of I2, it can happen that S of I2 updates its own hash table with A for aeroplane, and before syncing A for Apple from K1 V1. So in this case, S of I1 would see the updated state to be A and Apple, whereas S of I2 will see the updated state to be A with aeroplane as the key. So now you can see that clearly there is a conflict among which is the more latest insertion. So there are ways which we can handle some of these issues. For example, if the same client is sending, so we can associate a timestamp or a request ID with along with each request. So the system can resolve whichever of these two requests have the more recent timestamp. You can consider that to be the updated state. But note that like when multiple clients are sending this requests, let's say this query was sent by client C1 and this query was sent by client C2, and it might happen that the clocks of C1 and C2 are not in sync. And it can happen that although C2 send it let's say at a later time, but the clock of C1 was showing a later time. So this is like another problem that can happen with the replicated system, because it's not there is not a single server where I'm inserting the data every time. It's like we have multiple servers, and we are choosing any one of the servers for doing the insertion. So this is one other problem. So how do I overcome all these problems in a replicated systems? Uh, yeah. So in replicated distributed systems, there are applications depending on the requirements of this application. Uh, it is generally such that this application provides some consistency guarantees. So what do you mean by consistency guarantee? Consistency guarantee implies that for example, a strong consistency guarantee implies that when after I insert a key value pair in the system, in the and I'm requesting that key in my next query. If I'm requesting the key in my next query, I should get the most recent value for that key, which was inserted from the key value pair. So this implies that it's a strongly consistent system. So it observe that it doesn't concern about how the insertion and how the uh, uh, queries are happening. But it might happen that insertion happens in one place and query is taken from another server. So both are happening at a different server, but it does not bother with that. It only ensures that uh, the key value pair that I'm inserting, and if I'm querying the same key in the next query, then I'm getting the most updated result value for that key. So this is like consistent, strongly consistent guarantee. Another is that even there are like other consistency guarantees. For example, eventually consistent. So eventually consistent, what this implies is that the system will eventually be in a consistent state. For example, in the first scenario that I described, where I am inserting this key value pair into S of I1, and it took time to sync both S of I2 and S of I3 with the same data. So when when I was querying S of I2, I was not getting that key value pair, or I was getting some I will get some old value for that key if that key was inserted at an earlier time. But eventually, like after let's say 1 second or 1 minute or 1 hour, it is guaranteed that when I'm again querying S of I2, I will get the most updated value for that key. So there are systems which ensure eventual guarantee with basically a maximum time limit. For example, 1 second. Like most cloud-based systems, like NoSQL databases that are hosted on clouds like DynamoDB or Cassandra, they guarantee kind of 1 second eventual consistency for their applications. So this is what do I mean by consistency guarantee. So you can like upfront specify what do you want to offer. uh, Now coming back to the question of how to do the replication, and how to ensure that there are no conflicts and so on. uh, so uh, so generally, for replication to take place in a distributed systems, there are certain algorithms or protocols that are widely researched. These are known as the consensus protocols. So what do we mean by consensus? Consensus is nothing but it's like a kind of a majority voting. yeah, like in general terms, you can think consensus to be a majority vote. So there are like multiple consensus protocols available right now for many distributed systems. uh, One of the like the most famous and probably a bit more like complicated, difficult to understand is Paxos. So this is one of the consensus protocol that is widely used in distributed systems for replication. Another version of consensus protocol that is widely used is Raft. So Raft is quite famously used in many modern systems because it is like quite easy to understand and implement, and also to easy to reason about. So so the problems I just mentioned about replication, so those are actually inherent problems in distributed systems, and to like solve those, so it is not that all these problems would be unavoidable in any system, in one single system. It is how we want to configure our system, and what are our functional requirements for the system. For example, there are like multiple different ways we can configure the replication of a distributed systems. Okay, I'll just go through some of those configurations. I'll come back to the consensus protocol later, or I'll try to explain Raft in detail in probably another video. So, so for resolving the like basically the problem with having conflicts where we are inserting the data into multiple servers. So there are one configuration is probably having a single leader system. So single leader, in a single leader system, what happens that all the insertion or the writes for this distributed hash table will take place through only one server. For example, in this case, let's say s of I1, which we denote to be the leader for this partition. And s of I2 and s of I3 are replicas, and s of I1 is the leader, and all writes will happen through s of I1. So you can then see that there should be no more conflicts, because because the leader, which is s of I1, is in a consistent state always, since all the writes happen through it. So this is one configuration, but this has like a few drawbacks. For example, now what happens that if this leader goes down, correct? So this is what exactly the consensus protocol like Raft and Paxos also tries to solve, is do a leader election. Let's say in Raft we have a single leader system. So if this leader goes down, then there is an election that happens among the other replicas to elect a new leader, and then that new leader takes the place of the old leader. So there are leader election protocols for doing that in consensus protocols algorithms. So that is how probably we can solve the problem with the leader going down. Another problem, you can see that for a high throughput system where let's say the number of writes are very high. So and all the writes are going through the same server as in this example. So it would like overwhelm this single server. So and it could lead to like throttling of requests. So it's probably not a best solution when we have to implement a high write throughput system. Generally, uh, NoSQL databases like DynamoDB or Cassandra, they are most suited for high write throughput applications, and that is why they do not have a single leader system, but they are they are basically a leaderless, or you can or a multi-leader system. Leaderless, I can say that they are leaderless systems. So there is no single server which acts as the leader, but there could be multiple leaders, and each leader can have some replicas. So but yeah, the problem with the conflict still persists, and they have their own algorithms for resolving those. One thing to I noteworthy I want to mention is that the algorithms that this systems implement to resolve these conflicts, so it does not say that anyone. So when a conflict happens, so it can happen that either choice A is correct or choice B is correct. So, but it does not say which one is correct. So there need not be any one correct right that took place. So it only concerns about how to choose one of these, either A or B, and reason about that. So that is what the systems mostly try to like deal with when conflicts happens with a leaderless systems. So this is like one way where leader and leaderless, one configuration where leader and leaderless replicated systems, how they works. Another type of configurations that you can imagine is that uh, how replication happens. So replication happens can happen in a synchronous fashion. So in that case, we call it synchronous replication. Synchronous replication, or the replication happens asynchronously, which is asynchronous replication. So, what do you mean by synchronous replication and asynchronous replication, and where are these two types of replications are generally used? So, in synchronous replication, what happens? Synchronous replications generally it happens that when I'm sending a, let's say, a write request for the key value pair to be inserted into this distributed hash table. Let's say it comes to s of I1, it will insert the key value pair into the write ahead log, updates this in memory hash table, uh, and then what it will do, it will send a request for replication to s of I2 and s of I3, and it will wait for the response from S of I2. So S of I2 will also insert it into its own write ahead log plus update its in-memory hash table. Similarly, S of I3 will do the same process. So you can achieve this two in parallel using threads. Once both S of I2 and S of I3 are done with the replication steps, so they will send response back to S of I1 saying that okay, we have now inserted this to this key value pair, and now you are good to send the response back to the client. So now S of I would then send the response back to the client that the insertion is done. Insertion is done. Let's say I inserted one. So this is synchronous replication because the client is waiting for all the replicas in the system to correctly replicate the key value pair in its own system. So generally, in Raft, we can mostly like synchronous replication is used. What happens in asynchronous replication? In asynchronous replication, the client need not wait for all the replicas to be updated. So there are multiple ways by which asynchronous replication can be implemented. So one of them could be like that the client when it sends a request to the server S of I for I1 for insertion, S of I1 updates its write ahead log as well as the hash table and sends the response back immediately to client saying that okay, we have inserted, and in the background s of I1 will replicate s of I2 and s of I3 in the background, but it will not guarantee that both s of I1 and s of I2 were replicated correctly, because it has already sent that response back to the client, and there is no way to inform the client again that okay, there is some issue with s of I2, for example. So this is one way where asynchronous replication might happen. Another possibility could be that the basically there is some kind of a message queue here, message queue, uh, and when the request comes, it is inserted into this message queue, and the response is sent back to the client that we have queued your message. And then what happens, there is a, let's say, some worker process which would like this read the messages from the message queue and appropriately, for example, update the hash tables for all the replicas. So this is another type of asynchronous replication that might happen, where the client need not also wait for the leader server to, let's say, updates its own write ahead log and its in memory hash table. So it depends on like what does your application wants. For example, if we want a strong consistency guarantee, then synchronous replication is the way to go, because as you can see that in synchronous replication it ensures that all the servers are correctly updated. Now when I am making a get query in the next time, I am bound to get the correct, the most updated value for that query if I query any of these three servers. So it's like kind of a strong consistency guarantee with synchronous replication. Whereas in asynchronous replication, there is no strong consistency guarantee, and it's mostly eventual consistency, because it is not guaranteed that all the servers are replicated, and the client gets the response that the replication has been completed. But it might happen that when the client queries again with the same key as in the GET request, they might not get the correct result. So that's a trade-off we have to make, because although synchronous replication ensures a strong consistency, it is slow. As you can see that if there are n replicas, so the system has to replicate all the n replicas first before sending the response to the client. Whereas in asynchronous replication, the system do not have to replicate the n replicas. It's a kind of a O of one complexity with asynchronous replication, and they are very fast. So that's the trade-off we have to make while designing such replicated systems. Yeah, so these are like some of the configurations that one can employ to basically make do trade-offs based on requirements. So there are like other like replication strategies. For example, semi-synchronous. In semi-synchronous, what happens is that uh, so uh, so as you said, as I said that in synchronous, all the replicas are servers are first replicated before sending the response to the client. Whereas in asynchronous, all only one server or none of the servers are replicated before, let's say, sending the response back to the client. Uh, uh, can we find out some middle ground? So in semi-synchronous, it's kind of a middle ground between synchronous and asynchronous, where let's say if there are, like let's say, three servers. Let's, let's clear this a bit. So let's say there are three servers, uh, and we have SI1, SI2, and 2. And let's say in this case, the client waits for n plus 1 by 2 number of servers. Since n is assumed to be odd, because in replication we generally use odd number of server, so in this case n plus 1 by 2 is 2. So the client will wait for any two of these servers to send the response back to the client. So it might happen that during the replication with a synchronous strategy, let's say s of I2 and S of I3, that S of I2 is not responding, and it's like overloaded, whereas S of I3 has responded back. So the client will wait until S of I2 recovers and sends the response back to S of I1, and then S of I1 returns the response to the client. So that's probably a very I mean, like, time consuming process, more so if there are like more number of servers, like assume instead of three servers we have five servers. So any one of these servers would have a like overloaded system or a delay, and we have to wait. So it's basically the maximum time among the end servers that it takes to do the replication in synchronous. So we can find a middle ground where instead of waiting for all the servers, we can wait for at least n plus 1 by 2 servers. So if we have three servers, if there are two servers that have replicated correctly, the response is same. So in this case, for example, when the write request was sent, S of I1 updated its own hash table, so it is replicated. Next, S of I3 sends the response back to S of I1 saying that it has replicated. But although S of I2 has not yet responded because it is overloaded. Now we have two servers, S of I1 and S of I3, that have replicated the system. And so the S of I1 can send the response back to client saying that okay, the system has been replicated. So this is kind of a common ground. But why should this strategy n plus 1 by 2 strategy work? uh, note that if I'm doing a get request in the next query, for example, for the same key, I'm sending a get request. Now it uses the same strategy of choosing n plus 1 by 2. So I send this get request instead of send yeah, I send this get request to n plus 1 by 2 of the servers in this replicas, and I receive the response from the n plus 1 by 2 servers, and probably take the response which is the more latest. So we are storing kind of a timestamp with each, let's say, in right, a key value pair. So n plus 1 by 2 servers would send probably different timestamps depending on when those key value pairs were in, when that for value for that particular key was inserted. So depending on which is the latest, we can take that value. Why? Because why this should work? Because during write, you can see that s of I1, s of I1 and plus s of I3 were replicated successfully. Correct. Now during get request, what are the possibilities? In get request, the possibilities are that the possibilities are that I send request to s of I1 plus s of I3. I send request to s of I1 plus s of I2, or s of I2 plus s of I3. Correct. So let's consider the first possibility. In the first possibility, both S of I1 and S of I3 were updated correctly. So I am like guaranteed to receive the correct result from both S of I1 and S of I3 for, and the most updated value for that key. So this ensures me I get the correct result. Now S of I1 and S of I2. So note that S of I1 has been updated correctly, whereas S of I2 was not updated correctly. But I am taking the most recent value. So the most recent value for that key would be coming from S of I1. So since I'm considering the recent value, so I'll have the most updated value here. So I have the correct result. Similarly, for S of I2 and S of I3, S of I3 was updated correctly. So I will get the correct response. So as you can see, in all these three cases, I am getting the correct, most updated value from this system. But there is a trade-off. What is the trade-off? In the trade-off is that in a synchronous replication system, I am sending the GET query to only one of these clients or one of these servers, not all the three servers. Because during the write process, I'm guaranteed that all the three servers were replicated correctly. So I have to send the request to any one of these servers. But with semi-synchronous, it is not guaranteed that all the servers were correctly replicated, and that's why I have to send to n plus 1 by 2 number of servers the same request. So there is a trade-off associated with synchronous versus semi-synchronous. So yeah, so this is like another strategy that some systems use for their like replication of distributed systems. So in this video, I tried to cover only some of the fundamental aspects of a distributed systems, and they are by no means thorough. There are like multiple areas where which we have not like deep dived into. For example, understanding some details about the consensus protocols like RAFT and Paxos, or or how to basically efficiently implement the replication, like synchronous or asynchronous replication, how to coordinate between different servers using threads or processes, uh, or also like how to like do auto scaling. For example, if like a server in a replication system goes down, like how to like ensure that the server restarts quickly, or how to like add more servers to a replication pool, and so on. So all these are like different questions that I have left unanswered in this video to make it a short walkthrough for people who are looking to like understand basically the fundamental of distributed systems. So probably I like create other videos in the future where I like deep dive into some of these details, into in more. and explain more stuffs on similar things. Till then, I would say, like, good luck, and we'll see you next time.